Hello everyone, welcome back to another session on design of welded joints. In our previous video, we had an overview of design of welded joints and we have learned how to design the basic lap and butt joints. Here I will be extending our analysis to design of unsymmetric welds which are subjected to the axial load. So here you can see an angle section which is welded to another base plate. The angle section you can visualize it in the 3D here. So this is our L-shaped angle section which is welded to the base, and weld is provided in these two locations. So here the difference is the welds are of unequal lengths. This is in order to nullify any moments produced. That means if you are seeing this weld section will be having the cross section, you can see here in the shape L will be having a CG somewhere at this position, and along this point the force that is perpendicular to this figure or this plane load will be acting in this direction, or in this figure the load will be acting along this line, that means through this CG. So whenever this load is passing through the CG, the weld provided near this CG or this line will be taking more load, so that we will be providing, or the weld line near this location should be higher compared to the other thing. Anyway, these weld lines are of unequal length. So the CG will be, or the CG will be lying along this axis, so that this distance we can call it as E1 and this E2. They are proportioned in such a way that the moment created about this CG axis is 0. So based on this concept only we are analyzed. So I will be taking the figure to the next page. So here this is the thing for analysis where unequal weld lines are provided for attaching this L-shaped angle plate. So here when I am applying this force of P on this plate, so this is the force applied. So this is the force applied P. If this weld lines are of equal length on the top and bottom, then the share of the load taken by both will be P by 2, but it is not the case. Here load shared by both the upper weld of length L1 and length L2 will be different. I will be calling that load taken by both these welds as P1 and P2. This P1 and P2 will be different because the lengths are different. So you are knowing that this is a parallel fillet weld. From previous video we have studied that if the load and the weld lines are parallel, then you can call it as a parallel fillet weld. Here plates are overlapping, and in such case shear stress will be produced. You are knowing that. So and you are knowing that if you are multiplying the shear stress into area, then you will be getting the force, and in the design of weld you need to take this area as the throat area. That concept you are already knowing. So I can write the total load acting on the plate will be taken by these two parallel fillet welds at locations 1 and 2. So I can write P equal to P1 plus P2. This is one equation for our analysis, and we are knowing that the P1 load taken by the fillet weld at location 1, this I will be calling it as 1 and this I will be calling it as 2. So you are knowing that from this concept shear stress into area, this will be equal to shear stress into area of that location, and this is the throat area to be taken. So P1 equal to tau into A1 is HT into L1, that is the size of the throat, HT into L1. This I can write in terms of H. If the size of the weld in this figure, if you are seeing this side view, then you will be having the triangular section here. So this will be known as the size of the weld H. So I can relate the throat size HT as 0.707 H. We are already knowing this. Then I can write this as tau into 0.707 into H into L1, where H is the leg of the weld. So this is P1. In a similar way, this I will be calling it as equation 2. And in a similar way, P2 is equal to load taken by the lower part. The same I can write it as tau into again 0.707 H into the length of the weld L2. So these two values I can use in this one. And another equation I need to, if L1 and L2 are the unknowns, I will be needing two equations for solving that one. So another equation is, I already mentioned that along the CG, the moment taken by or moment produced by this load P1 and P2 are 0. That means here P1 is at a distance of E1 from the CG, that is given here, and E2 is the another distance. So this distance will be E2. So the moment created by these two forces about CG, or this line will be taking, or about this axis will be taking. So the moment created by P1 will be in this direction anti-clockwise, and that moment will be P1 into E1. Similarly, the moment produced by P2 about this will be P2 into E2. So I can write the net moment as 0, or the anti-clockwise moment produced by P1 into E1. This is anti-clockwise. This will be equal to the clockwise moment produced by P2 into E2. So this is clockwise. So from this I can write P1. You can relate these things. P1 by P2 is equal to E2 by E1. Like this you can write. So this is another equation that you may need for solving or calculating the L1 and L2. This is another equation 2. Sorry, I will be calling it as 4. That means if you are finding the ratio of 2 and 3 from here, 2 and 3 from here, then P1 by P2 will be equal to this L1 by L2. So this ratio will also be getting, and you can use the equation P for finding this one. So finally we will be requiring this equation. P1 can be expanded in terms of this term, P2 can be expanded in this term. So we will be having L1 and L2 unknowns. The same can be solved with respect to using this equation. So I will be solving one problem, or I will be demonstrating how to use this concept for solving such a problem from the unsymmetrical weld subjected to axial load. So let's get into that problem. So here a tie beam of roof truss that consists of an angle plate whose dimensions are given. 90 by 90 by 8 means this dimension is 90 mm, and this dimension is also 90 mm. So its CG will be coming somewhere here, and the location of CG or the axis is here, and that distances, that is the previous E1 and E2 values, are mentioned directly given here. In some problems it may not be given, then we need to identify the CG using the basic principles. I will be demonstrating a similar case in this video itself. And here the load applied on the plate is 125 kilonewton. That is the value of P1 is 125 kilonewton. And the design, here we need to design the joint if the size of the weld is 6 mm, that is H equal to 6 mm. Size of the weld is equal to 6 mm. If you are noting, this is the thickness of the plate, but here we are not using the same thickness as the size of the weld. Here size of the weld H is equal to 6 mm. That is the point to note. And here the allowable shear stress is 102.5 megapascal, 102.5 megapascal or Newton per mm square. And the distance between the neutral axis E1 and E2 are given. So here we need to start from the basics. The load applied P will be taken at this position. I will be calling it as P1, and at this position this is P2. So I can write P equal to P1 plus P2, and this P value is 125 kilonewton on left hand side. So I can write 125 into 10 raised to 3. And we are knowing that P1 equal to in the earlier page I explained, it is tau into 0.707 into H into L1. L1 is an unknown. So tau value is 102.5 megapascal into 0.707 into H value is 6 mm into L1 is an unknown. This is the first term. Similarly for P2 again, allowable shear stress is 102.5 into 0.707 into 6 into L2. So this is another thing. So if you are observing, I can take this right hand side as 102.5 into 0.707 into 6 into L1 plus L2. Like this I will be getting. On left hand side we are having 125 into 10 raised to 3. So from this equation you can find the values of L1 plus L2. So here L1 plus L2 will be equal to 125 into 10 raised to 3 divided by 102.5 into 0.707 into 6. So this value will be equal to 287.49 mm. Next I can have this expression that is based on the moment. P1 E1 is equal to P2 into E2. So P1 expression you can use this directly. That is tau into 0.707 into H into L1. Finally, if you are simplifying, you will be having L1 E1 is equal to L2 E2. This expression you will be getting. So from this one you can calculate L1 in terms of L2. So L1 will be equal to L2 into E2 by E1. Here E1 and E2 value are given. E2 is 61.3. So this will be equal to L1 into 61.3 and the E1 value is 28.7. So this is 28.7. So from this I can write 61.3 divided by 28.7 is 2.13. So this L1 will be equal to, this is L2. L1 will be equal to 2.13 into L2. The same thing I can substitute here and find the respective values of L1 and L2, which are the length of the unsymmetrical welds provided at the top and bottom of this angle plate. So L1 plus L2 is 287. So L1 is 2.13 times L2. So I can write this can be substituted in terms of 2.13 L2. So 2.13 L2 plus L2 is 3.13 L2 will be equal to 287. So plus 1, this is 3.13. The 287.49 divided by this answer will be giving you the value of L2, which is 91.68 mm. From this you can find L1. L1 will be equal to this minus 287. 287.49 minus this answer will be giving you 195.8 mm. So these are the answers for this problem that found the values of L1 and L2, which are the welds provided at the top and bottom. So this is the answer for this problem. So this is the way to solve this problem for finding the weld size or the weld length provided at the top and bottom. And next we will be seeing a problem. I will be showing the same expressions. You could have used the equations here in this data book. The unsymmetrical weld is given, the figure is given here, and the corresponding equations are given. So I have directly analyzed using the fundamentals. Here you could have used these expressions for evaluating the L1 directly from this one. So the anyway the both are same. Here I have started from the basics and here the equations are directly given. So the same thing I have explained. So this is the unsymmetrical weld. All equations are same, which is given the data book, equation 6.2. E, F and G. A similar problem will also be solved here. Here only the difference is here the eccentricity E1 and E2 values are not given. So we need to find the values of E1 and E2. So E1 and E2 are the distances or from the both the weld lines to the CG, or in other way it is actually the line, or it's actually the point where the CG is occurring for this cross section. So here we need to find these values E1 and E2 from this cross section itself. So you can find the value. So I will be marking this cross section here separately. So this is in this form, in this L shape, and the dimensions of the same thing are given 75. And here I will be finding our origin here, and the axes will be along this one for finding the CG. So this dimensions I will be marking. This is 10 mm. So I will be taking this up to this one part. So this is the first part and this is our second part. And the total length was 150. So here after subtracting this thickness, this will be 140 up to this point. And the thickness of the second part is 10 mm. So here I will be I have to find the distances, that is this distance for finding the E1. This is actually, if I am calling this as the x-axis and this is the y-axis, then I need to find the value of the y bar, that is from the x-axis. So I can use the basic equation y bar equal to a1 y1 plus a2 y2 divided by a1 plus a2. So this equation I will be using. A1 is actually area of first, that is 75 into 10, and y1 is the distance from the x-axis to CG of the first part, that is the half of 10. Anyway, it is 5 mm. So into 5 plus a2 is the area of this part, that is 140 into 10. So I can write it as 140 into 10 into y2 is the distance from the x-axis to CG of the second part. CG of the second part will be 140 by 2, that is 70. From here to here again we need to add this 10 mm. So it will be 80 mm. So this is 80 mm divided by A1. A1 is 750 plus A2 is 1400. So I can use the calculator for finding this. 750 into 5 plus 1400 into 80 divided by 750 plus 1400. So this will be getting around 53.84 mm. So this value is 53.84 mm means our E1 value is 53.84 mm. The remaining value E2 you can evaluate by subtracting it from the 150. So this will be equal to 150 minus 53.84 and that value will be equal to 96.16 mm. So now you are having the values of E1 and E2. The same can be used for solving in the similar way or to the previous problem for finding the L1 and L. So here again in the same method, here the load applied is P, which is 100 kilonewton. The load taken by this can be named as P1 and this will be P2. Then I can use the expression P1 plus P2 equal to P, and this is again our value tau into 0.707 into H size of the weld into L1 plus L2 equal to P, which is 100 kilonewton. This is one equation, and the other equation is P1 into E1 equal to P2 into E2. We have evaluated the values of E1 and E2 here. This is E1 and this is E2. Then you can find the value of L1 and L2, or you can use the equations from data book. Here you can use this expression for finding the value of L1 and L2. So because all other parameters we are knowing, so you can use this equation directly. Then because we are having the values of E1 E2, the load P applied is sigma, the allowable stress. This sigma should be read as tau because we are knowing that in parallel fillet weld it is actually torsional shear stress. So the sigma you can simply replace by the shear stress tau. H is the size of the weld and this B is the total distance. So you can use this one, or the method I have explained you can also use. So once you are solving, you will be getting the value of L1 as 76.93 mm weld length you will be getting, and for L2 the value will be around 43.07 mm. So these are the answers for this one, and you can add a 10 mm clearance for starting and stopping of the weld. It can be added to both these values. Anyway, this is the method to solve this simple problem from the unsymmetrical weld subjected to axial loading.